All right, sorry I'm late. Do you have any questions? All right. So to continue from where we left off last time, we were talking about Ito's formula, which basically is a way to express a function that depends on time and the Brownian motion in terms of a Riemann integral and a Ito integral. All right. So it's basically a fundamental theorem of calculus version for Ito integral. And the formula goes like this. If we have a function, okay, let's say is C12, that means one's continuously differentiable in T and twice in X, then the differential of F depending on T and the Brownian motion will be like this. Where these guys are differentials. Sorry, these are partial derivatives. And the integral version of this will go like this. Apologize, this is dt. Okay. And that was that. Now let's take a look at a few examples that we talked about last time, but let's do them again. So we could have something that purely depends on WT. So this has no T dependent. So in that case, we discussed that as a separate formula, but the understanding is that there's just no partial respect to T term. So for that, we got this is e to WT dWt plus 1/2 e to WT dt. So here, because we got the function is e to the x, its derivative and the second derivative are both e to x. The second example is, let's take the same form. Okay, well, hold on. So what is the integral form? The integral form, this will be e to WT minus 1 will be the integral like this. Okay. So the second example, we will look at this similar function, but now we introduce a t dependence. And let's suppose that a t dependence up here. Well, for that will be, right, so first there's a partial respect to t. So we got wt e to t wt dt plus, now differentiate with respect to wt gives you t e to t wt dwt, and then differentiate with respect to wt one more time gives you t squared e to t wt dt. Where, of course, what we look at is the function f of tx is e to tx, and the partial, right, with respect to t of f will be x e to tx. The partial with respect to x of f will be t e to tx, and the second partial will be t squared e to tx. Okay. And the integral version we'll skip. We'll just mention it's going to be the integral, etc. All right, just plug this in as we did above. Another variation would be where we put the t down here. So in other words, let's do the t e to wt. Okay. They're all very similar, but of course they are different functions, so they have different Ito's formula. And so for this one, differentiating with respect to t gives us e to wt dt. With respect to wt gives us t e to wt dwt. Differentiate with wt one more time also gives us t e to wt dt, where the function f of tx is t e to x, and so its partial with respect to t is e to x, partial with respect to x, and partial with respect to the second partial is also t e to x. All right. Any question here? All right. So these are standard equations. Now let's apply this to Black-Scholes formula. So we claim that, so the main point is this, we claim that the stock formula, the stock price follows this model if and only if its differential follows this. Or obviously this model is nothing but the percentage return model. Or the log return follows this model. So there are 3 points, 1, 2, 3. These 3 points are equivalent via the Ito's formula. Okay, so it establishes several things. It establishes that the log return is always below the percentage return. Second, given either the percentage return or the log return model, we get the stock price following this model, which is referred to as the log normal model. Because if you take the log of the price, you get a normal distribution. Okay. So our goal is to show that these are equivalent. So we do this by basically, we have done a lot of these works already, but this is kind of reviewing. So we show that 1 and 2 are the same by Ito's formula. Well, so for doing that is probably helpful. So basically, we apply Ito's formula to 1. And so for that matter, let's view ST, okay, as a function of TWT, where this function will be S0 e to the mu minus 1/2 sigma squared t plus sigma times x. So the t shows up right here, and the x term, which is the Brownian motion term, shows up there. Okay. So we do this because certain calculation doesn't have to kind of like be written in a long form like this. For example, the partial respect to t of f is what? Well, we just bring this guy down. We just bring this guy down. Everything else is the same, which means that it's just going to be mu minus 1/2 sigma squared times f. The partial respect to x, we just bring this guy down. So it's sigma times f. The second partial will be sigma squared times f by the same reason. So that is almost all of it. Because then by Ito's formula, dst will be the partial dt. But of course, when you plug in the Brownian motion, this turns into the stock price. So that's just 1/2 sigma squared st dt. And then similarly, this would plug in the Brownian motion, we got st dwt. Finally, we got the last term. And we observe exactly the very, very nice thing that this part and this part cancel, leaving us with mu st dt plus sigma st dwt as claimed. All right. So some of you may think that, well, this this procedure may be more like 1 implies 2 only, because it's not clear how to go back. It's not clear how to go back, meaning if we start from here, it's not clear how we can integrate up and get this expression. So in other words, if we're given this, it's not clear how we're going back. The reason is, unlike the examples we did above, right? Basically, everything we did above, for example, the left side and the right side just involve t and the bar motion, which are supposed to be known. Here, st is a mysterious object, okay? It's like a function, a mysterious function. If we kind of follow the integration blindly, right, which is fine, if we try to go recover 1 from 2, okay, then what it says is this, okay, take this. What it says is st minus s0 is the integral mu, let's say s sub u du plus sigma s sub u dwu. That clearly is nothing similar to what we claim, which is this. All right. So somehow these two integrals resolved into, well, so somehow or let me say y, right? So if you transfer S0 over here and add, it's supposed to be equal to this expression. So that's sort of like the mystery that we're addressing. Okay, so the reason is simple actually. The reason is the integration here still involves s. So it's not purely just an integral in terms of t and wt. It involves the unknown s that we're looking for. Okay, because we claim that st is equal to this and also equals to this, which is true on both counts. But when we express something like this, it unfortunately doesn't have much meaning because the unknown object is still on one side. Okay, so the phenomenon we're observing is something called a stochastic differential equation. Where we have the function, okay, showing up on both sides of the equation of the differential. And exactly the relation between 1 and 2 is the relation between a differential equation and its solution. 1 is a solution to the differential equation because 1 solves explicitly for st without invoking anything about st on the right-hand side. It all involves t and wt. Okay? So, any question here? The relation here is actually exactly similar to the following, which you should have seen in differential equation. So we can take a look at a function in t, for example, and say this. Okay. Well, what does this mean, by the way? This means or usually expressed as f prime equals to f. We all know what this solution is. This solution is f of t is f of 0 e to a t. Okay. And obviously, so this is the version number 1. This is version number 2. So this is the differential form of this expression. This is the solution. Okay, and you see that if you differentiate 1, you get exactly that f prime is f0 e to a t, which is exactly f. So that checks out. So 1 checks out 2. But on the other hand, if you take 2 as a starting point, all you got is, if you start from 2, then all you got is f of t minus f of 0 is the integral, all right, of f of s ds, which is also true, but that does not exactly recover the expression. Okay, so that's what we're observing right here. That's what we're observing right here. Okay, and so of course, I mean, differential equation requires some techniques to solve. All right, it takes some step to somehow show that if you're faced with this equation, you would get the solution to be this. So same thing here. All right, by applying Ito's formula, we do verify that if ST has this formula, all right, if ST has this formula, then it exactly satisfies this equation. But conversely, going from here back to step 1 is not a direct integration step, but that's okay, all right? Because by differentiating and verifying that the formula holds, we verify that this is indeed the same. The derivative of ST is indeed this. Any question? Okay. Now, what about the relation between 3 and 1? The relation between 3 and 1 is actually a direct integration relation, all right? Because you can integrate this guy right here. So let's say 3 and 1. Relation between 1 and 3. So again, to remind you, 1 says ST and 3 says the log return is this. Sorry. No ST, sorry. Just this. Okay. The relation between 1 and 3 actually is very easy. And in fact, we go from 3 to 1. How? Well, you integrate both sides of 3. Okay. And these are all differentials, and adding the small changes give us the big change. So here we got log st minus log of s0 is integrating the right hand side is easy. Okay. And so this is nothing but log of st over s0 and so we can multiply, we can exponentiate and multiply, which exactly gives us what we need. Now, what's remaining? What's remaining is actually, first of all, to observe that, well, even though we say 1 and 3 are equivalent, because exactly we can integrate 3 to get 1, it's not exactly clear, right, that, again, differentiating 1, we get 3. Because as we show above, differentiating 1, according to Ito's formula, you get 2. All right. So it's more like we show that differentiating 1, we get 2. And integrating 3, we get 1. All right. So actually, sure, that's fine. And actually, if the circle does go both ways, the reason is if we can integrate to get this object, then it should be that this object somehow gets the other one. But all right, if you want to follow the strict chain of differentiation that we did, differentiate 1, we get 2, integrate 3, we get 1. Okay. So it remains to show that somehow 2 and 3 are related, and then we're good. So somehow if we can go from 2 to 3, then we could close the loop. I mean, without even having to appeal to some obvious thing that, integrating, differentiating are the same thing. So it remains to show that 2 and 3 somehow are related. Okay. Well, what does that imply, or what does that require? If we stare at it for a little bit, 2 gives us some differential of S. 3 gives us the differential of log of S. That's awfully similar to what Ito's formula is trying to do. Ito's formula says that we can find the differential of a function of Wt, like this. Okay, so what we want to show, right, is somehow 2 implies 3, and then we're good. So in other words, we start out with the differential of St, and then we want to show that this says that the differential of the log is this. Okay. And this is very similar to Ito's formula in this way. So if you ignore all the bells and whistles and suppose that, we only have the Wt term, then we start out with basically Brownian motion and this differential. And then we want to look at the differential of the log, which actually we know how to do because this will be by Ito's formula. It's just this. Where, of course, the function that we're looking at is natural log of x. And the derivative is 1 over x. The second derivative is minus 1 over x squared. All right, so it's awfully similar, but of course, right, we get something more complicated to start with. It's not just pure Brownian motion. Basically, we start out with something with dt and dwt as well. So how do we fit that into this framework? So that requires us to extend the Ito's formula one more time. So we will do an Ito's formula that is the most general. So it's like the chain rule, if you will. So what we want is something like this. Suppose that we start out with something pretty general, like this, where mu t and sigma t are some, given processes. All right. So basically, this is given. So what I mean is exactly like this. So here, your x is the s, the mu t is this, and the sigma t, sorry. The sigma t, okay, is this guy right here, okay? And so something like this, xt is called an Ito process. All right. So it's like a generalization of the Brownian motion. Because if you take mu t equal to 0 and sigma t equals to 1, then we got xt is the Brownian motion itself, okay? Supposing that it starts at 0. All right. So now what we want to do is we want to exactly find the differential of some function of time in x, okay? Where f of tx is a C12 function. Okay. And the formula should not surprise you because it follows very much the same as the previous one. First, you differentiate with respect to t dt. Then you differentiate with x, but instead of dwt, we got dxt. And instead of dt, we got something like this, where at one point we did introduce this, is the quadratic variation of x. And in this case, this is very easy to find. The differential of the quadratic variation is sigma t squared dt. Okay. So the reason is like this. Roughly, all right. Roughly speaking, the quadratic variation is like dxt times dxt. Okay. So if you remember, right, this is like dwt times dwt. So this is like dxt times dxt, where what is dxt times dxt? Dxt is something dt, right? Well, we can write down mu t dt plus sigma t dwt, and then mu t dt plus sigma t dwt. And so what you got is something like this, something dt square, something dt dwt, and finally you got sigma t squared dt. Oh, sorry, let's do it slow. Sigma square t dwt square. Okay. And if you remember that dt squared is equal to 0, dt dwt is also equal to 0, and dwt squared exactly is dt. And therefore, that explains why the quadratic variation, or this term right here, is nothing but sigma squared t dt. Okay? And the further reason why this is true is because they all kind of boil down to dt raised to 1 plus epsilon is equal to 0 for any epsilon positive. And so dwt is, roughly speaking, dt to 1/2, because the quadratic variation of the biomotion is dt. So therefore, this is like dt to 3/2, which is 0, and this is like exactly dt. Okay. So all in all, we can reduce this formula one more time, or make it more explicit. To recap, suppose that you have an Ito process like this. Then the differential of a function will be f sub t dt, f sub x dxt will be mu t dt plus sigma t dwt. Okay, this whole thing is dxt. And then 1/2 f sub xx sigma squared t dt. And this guy is the quadratic variation of xt. Any question here? All right. So for example, and exactly the application we're interested in, we start out with the Black-Scholes model. So in other words, this is our mu t, and this is our sigma t. Then the log, okay, will be 1 over st dst and then minus 1 over st square, and then sigma square st square dt, where obviously we look at the function 1 over, log x, and the derivative is 1 over x. The second derivative is minus 1 over x squared. Notice how this is very similar to this, all right? But this is, of course, simple because we start out with wt. This has a bunch of things attached to it because we start out with dst. But essentially, it's still 1 over whatever that is times the differential, and then 1 over minus 1 over the square of it times the differential square. Okay. And so now to clean up, right, notice that things cancel out nicely, giving us exactly what we want. So this is exactly 2 implies 3 in our above scheme. Any question? Okay. So just let's do some more example on this thing. Suppose that we have xt is t plus wt. All right. Suppose xt is t plus wt. What is, let's say, the xt square? Well, the xt square will be 2xt dxt plus, right, 1/2 times 2 the quadratic variation of xt. Where what is dxt? You can see from here that dxt is dt plus dwt. So in other words, it's going to be 2xt times dt plus dwt plus dxt, right? The quadratic variation of xt is just dt. So just plus dt. So in other words, right, it's going to be exactly 2t plus wt dt plus dwt plus dt. Well, that looks a little bit kind of confusing, but if you combine the dt term and the dwt term, what you got is 2t plus wt, right, plus 1 dt plus 2t plus wt dwt. Okay. So any question here? We obtained this, right, from our last version of the Ito's formula. This one. But nothing, because x here is a very simple expression, okay? So this is using, right, this is the last version of the Ito's formula. But there's nothing, well, because xt is very simple, we can look at it from a different angle. Alternatively, okay? Alternatively, well, xt squared is t plus wt squared. And we know how to handle this from just the Brownian motion point of view. So we can do this, right? We can do this. D of t plus wt squared equals what? Well, if we view this from the Brownian motion point of view, then first we differentiate with respect to t, giving us, right, 2t plus wt dt. Then differentiate with wt, giving us 2t plus wt dwt, and then differentiate twice with t, right? Differentiate twice with wt. So if you differentiate twice with wt, you bring down the 2, differentiate one more time, you only get 2. So that's going to be 1/2 times 2 dt, which is exactly this guy right here. Okay, but do appreciate the point of view here. The point of view here is the old Ito's formula, where we used f of tx is t plus x squared. And so the partial with respect to t is 2t plus x partial with respect to x is 2t plus x. The partial with respect to x twice is 2. Okay. So here, right, here we use the old, I mean, not that old, we use the old Ito's formula, dftwt. So here we use the version of dfxt. All right. Again, right, the point is that no matter what version you look at, they get the same answer. They get the same answer. Okay. But notice that the function that we used are very different. Here, the function, right? The function is just a pure function of x, which is x squared. Because we look at dx squared, okay? It's the process that's complicated. On the other hand, down here, the function is complicated because it's 2 plus x squared. The process itself is simple because it's, you know, whatever that is. It's just a Brownian motion, all right? The process itself is just a Brownian motion. But, you know, all these formulas are consistent. Whichever way you want to apply is fine. But right, I mean, it just gives you different tools to deal with things. Any question? All right, so then maybe one point to address is this, right? Why the last formula? So in other words, why, you know, it seems like a lot of things can be handled using the traditional Ito formula based on T and WT, because everything depends on WT anyway. Why introduce the dfxt or ftxt, which makes things more complicated? Okay. The reason is this. The reason is it is most suitable when we have in the stochastic differential equation scenarios. Okay. Is the most suitable there. For example, so what do we mean by this, right? Again, remember, right? The Black-Scholes formula actually is a stochastic. The Black-Scholes model is a stochastic differential equation because you have the stock price is differential. It's like this. Okay. In other words, if you look at things like this, the stock price itself is a mysterious object that somehow show up on both sides. Okay, so it's an equation again, right? Because the unknown object shows up on both sides. Of course, financially, we say this describes the percentage return, which seems to somehow, right, get rid of the unknown on the right-hand side by passing it down to the left-hand side. Well, that's all fine and good, except that this right here, okay, pay attention. This right here is not a differential. In other words, it's not a change of anything, at least not directly, okay? Because here is a change of the stock price divided by the stock price itself. It's not a D of something like this. And again, I know that for you, everything is like a mixed bag of symbols, but these things have very different meanings. A differential you can add, because a differential means that you can sum it up to recover the net change, which allows you to recover the original value. If it's not a differential, it's unclear how to add these guys. Adding these guys makes no sense at all because you're not adding small changes, all right? So when you think about it, one wonderful thing about log returns is that, okay, so let me say this, and I'll connect with the financial meaning. Compare this with the log differential, the log return, okay, which is this. Okay, this right here is a differential, meaning you can add it. So what it means financially is like this, okay? Financially, suppose you have two periods, period 1 and period 2, all right? Suppose you have percentage return and then suppose you have log return. And remember, right, percentage return is always slightly higher in real life and in math. So let's say you get 4% here. Let's say you have 3% here. Let's say you have 3.5% here. And let's say 2% here. And let's say this is the first half of the year and second half of the year. Then I can confidently say that your annual log return, which is the total, right, between the two periods, right? So this is first half, second half. Your annual log return is 5.5%. Easy. Your annual percentage return, I don't know. You understand? Because these guys don't make sense to add. They're not differential. Adding percentage return of separate parts don't give you the big percentage return, no. But adding log return, right, gives you the total log return. You understand? Any question here? So, all right. So basically, obviously though, right, back to the mathematical aspect of things. We have shown that this and this says the same thing. But, right, exactly that, pretend with me here that you do not know the explicit formula for ST. All right, and that actually is an accomplishment. You start out here and you want to somehow convert it to this to log return. Not knowing what ST is, then the only thing available to you is the last Ito formula. Because the last Ito formula allowed you to operate, okay, with the differential, not knowing what the explicit solution is. You can go from here to here in a split second without knowing, okay, what ST really is. And that's very useful in practice, as I show you. So this allows you, right, the last formula allows us to differentiate without knowing the true solution of the equation. Okay. So again, let me show you a calculus example, and let's take our good old, logistic growth equation, y prime equals to y. We know the solution here, right? But pretend we don't. Suppose that, so this is the derivative, right? Y is a function of t, right? And what we're saying is differentiate y with respect to t, we get y back. Okay. Well, suppose that someone say, okay, I don't care. I just want to know, what if I differentiate y squared? What do I get? Okay. So now if you say, well, I don't know. I don't even know what y is. Why do you ask me this? Then you're giving up too much, because you do know, okay? You can say something about this based on this result. Why so? Because exactly by the chain rule, it tells you that this is going to be 2y prime. Okay? 2y prime. That's the chain rule. Well, but what's y prime? Y prime is y. So in fact, you know that this is 2y squared. 2y squared. You know that, whatever y is. Now let's see that it is true with the real solution. Well, the true solution of this is something like, let's say a constant, right? E to a t, right? So what's y squared? Y squared is c squared e to 2t, right? So if you differentiate y squared, what do you get? Y squared prime, right? Here's c squared times 2 e to 2t. But isn't that 2y squared? Right? So the point is, right, you can operate with differential in the dark without needing to know the solution. That's the virtue of the last formula, the last Ito's formula. Any question? Okay. So let me demonstrate the idea for you like this. Okay. That the Black-Scholes formula is not the only formula, or the Black-Scholes model, if you will. Sorry, not formula, of course it's model. Black-Scholes model is not the only model that employs time invariant motion. So the Black-Scholes model is the which of course we know is the same as saying the stock price has this formula. All right. And I think some of you may complain and say, you know, we've been wasting time discussing this guy and all the weird Ito's formula stuff, because why don't we just work with this? After all, right, it's a stock model, and I just need to take expectation. Why go into all this, blah, blah, blah details? Okay. And you should ask that kind of question, because every time you learn some tools, either it should have theoretical interest or practical interest. Okay. So yes, you see that indeed applying or knowing this structure is enough for you to do pricing as we've been doing so far, all right, in the binomial tree model. In fact, you see the whole binomial tree model is about expectation, about probability. It has nothing to do with calculus. But of course, that's very, I don't know, obvious too, because the binomial tree is discrete time. There's no calculus there. There's no continuous structure. But then that doesn't mean that suddenly when we move to continuous time, then somehow we need to involve ourselves with the calculus. We involved ourselves with the calculus not exactly to handle the Black-Scholes model, even though yes, right, there are something very, very interesting to learn about how the percentage return and the log return interact. And I think that in itself warrants, okay, knowing the EDOS formula already. Because again, right, the phenomenon that log return is below percentage return is a very, very significant phenomenon when you do accounting, for example, in finance. But right, a even more relevant example is this. It's just the same thing as why do you study calculus or why do you study differential equation? I mean, after all, right, why don't you just say this is, you know, so yeah, the question is, so why differential equations? All right, I'm not even discussing this class. I'm discussing some class that you should have taken some time ago. Why differential equations? Why Newton's second law? Okay, why those things? Because again, right, I hope you recognize that Newton's second law is a differential equation. Okay, or my double prime is some function, some force of time. So, right, why not, let's say, describe things as a function, right? Why not, let's say, y of t is e to 2t plus 1 or something? Why bother doing something like this? The answer is phenomena in life, okay, or the model, the way we model things, the way we observe things is through change and not through its explicit value, okay? We observe phenomenon through change. And not through the explicit value. Okay. Let me take an easy example. Like, and Newton's formula is something like that too, but a little bit more complicated. Let's look at your saving account. Okay. Let's say that suppose you deposit $100, and let's say the rate is 2%, right? We all know this. Let's say compound continuously. Okay, so 2%, this is the annual rate, right? And so what is the, how much do you have, right? By 1 year. Now I know this is a routine question that even like a, I don't know, a freshman student in a non-calculus class knows how to do, right? The answer is 100 e to 0.02. But actually, there's a lot of cheating going on in this answer. Actually, the cheating is exactly how you know this. Where does the e come from? Okay, and in fact, right, everyone would say, well, that's what the formula says, or that's what the textbook taught me, which actually explains nothing, because, right, again, where does this come from? Why e? You could ask a silly question, why not 2? Why not square root of 2? Why e? Right? And so you see, this is a magic act that hides a lot of things behind the scene. What really happens is, right, if you really observe what's going on with this statement, what it says is if y is the value, right, of your saving account at any time, then at every split moment, saying that it earns interest rate of 2% means that at any split moment, it will gain 0.02 of its current value multiplied with the duration of time that has gone by. This is what I mean by we observe things through their change and not their explicit value. We don't observe this, we observe this. And of course, right, if you push the notation together, you got y prime equals to 0.02y, which you, of course, recognize that that's exactly the, logistic equation I've been talking about. So then, right, differential equation is the technique to tell you that y of t is y of 0 e to a 0.02t, which allows you to plug in and solve for this. Okay. But so to recap, right, the y differential equation is the tool to allow you to solve the model of real life that you observe through change. Through change. Okay. Change, I hope, right, this little demonstration showed you that change directly involves differential or differential equations. And so therefore, right, you want to learn how to deal with differential equations to recover the value, if you will, right, from observing the changes, okay? So that's that. The same thing happens when we move to the stochastic realm. Nothing changed in the philosophy of observing the change, actually. It's the same philosophy. The only thing additional we have, and the only thing that mathematically makes things more interesting, is a shock, okay? Is the Brown motion component that represents trading actions, market shock, that kind of thing, market noise. But if you stare at this formula for a little bit, you see that, right? This right here is exactly this right here. What we're missing is just a y dwt component. But obviously, we don't have that. Why? Because this is a saving account. That's why you do saving account. You're not trying to get any shock, right? I mean, here, right? This is exactly saying dy. You have seen this many times. dy is 0.02 y dt. Okay. If you want to be more dramatic, you can say plus 0 y dwt. 0, right, means that there's no volatility. There's no shock. I mean, obviously, this is a saving account, like I said. But that actually explains the Black-Scholes model. The Black-Scholes model say, let's take a growth rate that you always know, right, and add a shock component to it. And notice the shock component exactly follows the growth rate component, of course, with a different rate, and that rate we call the volatility. And of course, with a different kind of shock, right? It's not the time component, but the Brown motion component. But all in all, you see this right here is a very sensible model for the stock price. This right here, God knows what. In fact, right, if you stay and stare at this, the intuition from this is very, very little. You can say, yeah, that looks like an exponential growth model, but from where? Okay. And what does it mean? Why the minus 1/2? Like, this poses more questions than it answers intuitively. I know, of course, I work with this, and I will just, when we do expectation, this is what we do. But to understand, okay, what we're saying about the behavior of the stock, the differential says much more. So I would argue that this is a Black-Scholes model. This right here is just some after effect where we recover the explicit value, the explicit solution where we can. All right. Any question? Notice also, right, that say again, this model says a lot more than catch the eyes. It says something, I think, which I mentioned before, that it says a stock will fluctuate more when the price is high compared when the price is low. Okay, where does that come from? You should have heard this, from just offhand financial observation, right? So if you hold Amazon stock, a swing in a day for you can easily be $50. Or if you hold, I don't know, some small company stock, each day you may swing $1, $2. Okay, why so? Well, if ignoring, right, the volatility and things like that, in fact, actually, an Amazon stock should have lower volatility than a small company stock. But this level of Amazon is very high, right? ST right here for Amazon is like 1,000 or so, or a small company, $10. So the 1,000 right here, right, is the same brand motion, same shock. It magnifies through the $1,000 level to give you a quite big of a shock, even with a small swing in the market. While if it's a $10, magnify through the swing in the market, not much going on in terms of the actual value. But the percentage, right, is a different question. That's why percentage return tells you a better story, because when you normalize, right, by the value of the stock, then it all boils down to a volatility level. So things become clearer that way. So people don't really look at, right, the change in price, they look at the return. But still, if you want to discuss the price level itself, there are things to be said. Okay. Question. So finally, okay, I want to mention two models that we'll see later. At the end of the course, models for interest rate. Okay. I bring this up because they are, at first glance, they are very similar to Bryan motion, except that they're not, and one of them will not have solution. So the first one is called the Vasicek model, where it says that the interest rate, okay, will be mu minus RT dt plus sigma dWt. The second is the CIR, Cox, Ingerson, and Ross model, where it says dRt is mu minus RT dt plus sigma square root of RT dWt. Okay. So here RT, right, is the interest rate. At time t. And you see immediately, first of all, these two models generalize and make, right, the constant interest rate that we always assume to be R, right, much more interesting. Because now, not only that we say the interest rate changes with time, we say that it's also random and is subject to some kind of market shock. Okay, but that aside, all right, that's to be later. We're still dealing with stock and option pricing for now. Okay, until like at least like 1 or 2 weeks later. But the point is this, though, that notice that the structure of this is quite close to the Black-Scholes model, right? Quite close and also quite different, I think, right? It's similar in the sense that it has a DT component and a DWT component. But then, right, I think that's where the similarity ends. So in that sense, both of these models use the concept of the Ito process, okay? The Ito process. Where did we introduce it? The Ito process, right? The concept of the Ito process to model the interest rate, okay? So both of these models use the differential forms to model. Because exactly, right, you would immediately probably, you're curious, what's the interest rate here? Okay, why so mysterious, etc. Well, here's an answer for you. You could give an explicit answer here for Vasicek. As far as I know, there is no explicit solution for CIR, okay? Which is quite simple. Not every differential equation has explicit solution, which you should know that from, learning about those things. So this question is almost like irrelevant in a CIR model. There's no such thing. This is all we have to work with, okay? And even with Vasicek, as you see, even if we can solve for this, and I will demonstrate to you how to solve it, out of the interest of applying Ito's formula. But in practice, a lot of times, knowing this is not as relevant as looking at this, okay? So that exactly explains why, okay? Ito's formula and all those rules are much more important to us than knowing an explicit solution, because you want to pose an interesting model, you're not gonna, pose it through a explicit formula, okay? And so for that reason, I guess this says the CIR model is more interesting than Vasicek. I don't want to say that, but here is something for you that I'll end at this note. That CIR model has a very interesting feature, that the interest rate in CIR will always be non-negative, which I hope you say that's so what, right? Interest rate must be non-negative. Yeah, of course, in real life, maybe, but of course, if you follow finance closely, there are examples in history, right, that interest rate has gone negative before. So that's not even true in real life, but mostly true maybe. But also, in terms of modeling, you never know. You put down something that is guaranteed to be positive. Case in point, the interest rate in Vasicek can be negative. All right. And what really is the guy that explains that is this term right here. So this term is what guarantees the CIR model to be non-negative, but also what makes it more complex. All right. The Vasicek can be negative, so it's quite simple, but it will, what do you want to say it, right? It has the defect, if you will, of being negative. All right. So all in all, point being is, right, without looking at the differential version, we won't be able to tell these kind of things. And the cost of making a model more interesting and more workable is that you may have to forego knowing what it is explicitly. All right, we'll continue with this next time, and then we'll go back to the Black-Scholes model, Black-Scholes formula pricing. All right. Okay, sure, sounds good. Yeah, see you.